All right, so we got some homework coming due tomorrow. There's 4 of them, I think. So let's see what we got. I don't have too much here, apparently. What's going on with this time? Do that? No, you don't like that. Okay, we'll go here. All right. Got that homework to give back. All right, so let's see if we got any questions on this homework here. All right, we got some of this calculus stuff first. So now the important thing there is set up the relationship first and then set up an integral usually, and then you take a integral and then you're able to relate the variables together is generally how that works. You do want to pay attention to your limits on this stuff. That's often an important part of it, is to do that. So 122, do we got any questions on that one? 122. We're doing all right on that? I mean, yeah, there's a few things you got to do on this. We just want to find the velocity, acceleration, and position when the time is 4, right? And we got the velocity of the car is 0.3 t squared. So, what you'd want to be doing with that is, you've got the velocity is 0.30 t squared. If you take the derivative of that, you'll get the acceleration, which is dv dt, right? And so that would be the next thing you do, and you'd solve for the acceleration. Then you'd plug in 4. And then you'll get the acceleration at time of 4 is 2.4 meters per second squared. Here you'll plug in t equals 4, okay? And you'll get that v at time of 4 is 4.8. And then the other one, you want to understand that what v is the change in displacement with respect to the change in time. And v is 0.30 t squared is what it is. So you're going to want to work with that. So that's kind of the first step. The next step is to do that, right? And then you add them up over an interval. Now you do want to be careful over the numbers you put in there. I usually put letters on the top because that gets me where I want to go. Okay. So watch your limits of integration on that. And then when you go ahead and run that, you should get that S is equal to 0.10 t cubed plus 8, I think. And then plug in t equals 4. And you'll get that S is 14.4 meters. Okay. So that's just kind of using these basic calculus relationships. What you can see when you do this step here is you've got variable acceleration. And if you've got variable acceleration, there's 3 relationships that you can use. A is ds over dt. Excuse me, v is ds dt. A is dv dt. And then ADS is equal to VDV. Okay. And so you just use the relationships that are appropriate there to solve the thing out. You know, I noticed the basic relationship that I'm starting with here is that V is 0.3 t squared. So what I've got there is the velocity as a function of time. So that leads me to look at those relationships there that I could use. Here I've got the velocity is times dv and a is times ds. I don't really see a way to use this one to work with v equals 0.3 t squared. So I'll stick with the 2 on the left to work through that. Use the a dv is equal to dv dt to take a derivative, and v is ds dt to do an integral. So what we're doing here is we're doing this kind of classic little thing that we seem to do a fair amount of. We're setting up that v is ds dt, and that's equal to 0.3 t squared. What you can then do is get those differentials turned into regular variables by splitting the differentials. So leave the ds here on this side, take the dt to the other side, and I forgot that dt, didn't I? Whoops. So why don't I get that in there? There we go. There should have been a dt there. That came over to the other side, just like you would do in algebra. And what I'm doing there, I'm integrating ds on the left and 0.3 t squared dt on the right. I'm matching the variable, the 0.3 t squared. I consider that to be what I call the variable, I guess. I'm matching that with the differential, and when I do that, they both match. They're both t's. I can integrate. They relate to each other, so I can integrate. Okay. Now, when you do this, watch your limits of integration. Okay. You should put in things that match. So you want to look at when t is 0, what is the corresponding value of s? Those are the limits that go in. Okay. So we got any questions on that? Okay. So that's the basic approach on that. Be sure to pick the proper calculus relationship and watch your limits. Okay. Now this next one here, you want to be kind of a... Oh, the wrong problem number. I think you're right. I've rearranged all these. This is 123, isn't it?
No, it's particle accelerator. Yeah, that's right. It's the same problem, but it's
different number. Yeah, this one should be number 123. Yeah, okay. Sorry about that, but yeah, I've kind of played around with these over the years, so that's 123. Thanks. Okay. Now, the important thing here is this S does not mean seconds. It means S for displacement, and that's kind of unfortunate, but S is the variable that's used for displacement. So we've got A is equal to 0.12 times whatever S is, S being the displacement. Okay. Now that's the kind of the fundamental relationship that you start with on that. So S is the displacement in meters. Okay. So I'm noticing there that the acceleration varies as a function of displacement. So I'm going to go through, I've got variable acceleration. So again, I've got these different relationships that I can use. And what I need is something that essentially matches here, you know, that works into the equation. And, you know, you just can't force these things into any relationship. You have to have one that matches the variables you're using. Okay, now both of the ones on the left relate to time, but notice that this does not relate to time. It relates to displacement. So these aren't going to work. You can't just take this thing and put it into those relationships, because you end up with a dv, a dt, and an s and stuff like that. You just can't do much with it, okay? All right. So you want to use the relationship on the right because you've got the acceleration as a function of displacement. Okay? So what you'd want to do here would be to go ahead and plug the stuff in, you know, 1.2 s ds is vdv. Okay, and then you just add them up. Okay. Now, once again, you know, I always just put letters at the top, and then I put variables on the bottom. Or not variables, I'm sorry, so the variables, the letters are on the top, and on the bottom, I put in matching values, corresponding values, whatever you want to call them. Okay? So what you're going to want to do is find something in the problem statement that tells you what the displacement is and what the velocity is at a given instant. Okay? That correspond to one another. And you'll plug those in for the lower limits. And then you'll go and run the numbers on that. Okay? Now, be a little careful about just kind of throwing in the limits after you've done the integration. It's safest to put them in as limits into the integration. Sometimes people will just say, okay, you know, it said when such and such is 0, this is 6 or something. They'll just plug 6 in after they do the integration, but that doesn't always work. You got to be a little careful about that. What it is literally is it's a limit. It goes at the bottom there, you know, and you're looking for two corresponding values that occur at the same instant. Okay, so when you get through this, you know, I don't know, you might simplify it differently than I did, but when I did this one and I got through it, what I had there was 0.6 s squared is equal to v squared over 2 minus 0.32. Now, you know, you might work through it a little differently than I did, but that's what I came up with. And then you just plug in the known, or the thing you're looking for. You're going to plug in s equals 7. And when you do that, you can solve for v. It's 2.55. So we doing okay with that? Any questions on that bit? Okay. Yeah.
Where does the 0.32 come from?
The 0.32 comes from the limits. So when you plug in the limits and work through that, you'll end up with that constant there. Yeah, the 0.32 itself isn't one of the limits, but there's a number you put in for a limit that will get you down to that.
0.8 squared divided by 2.
Something like that. Okay. All right. So we got any other questions on that? Okay. So this is just something that comes up, you know, in some of these problems, this whole calculus business. So we just want to kind of get comfortable doing that. Okay. All right, now we get into the curved motion using Cartesian coordinates. Okay, so when t is 0, a particle starts to move from coordinates 0, 4. Its velocity is described as follows. So you got Vx is 2 and Vy is 2t. Write an equation for the path of the particle and plot it on the graph. Okay. So what you got to do on this one is you've got to kind of get back to a relationship directly between x and y. Okay, that's what the path is. Y equals fx. Okay. And you got to work with the information you're given to get back to that. So these are, I think they're called parametric equations. What you're going to want to do is solve x and y in terms of t and then relate them together. That's the approach you use on these. All right, so what we've got here, for instance, I'll just do one of them. We got Vy is equal to 2t. Okay, you're given that. Now, there's, like I was saying in class, there's a few of these little steps you want to go through. Dy dt is equal to 2t. Right? You okay with that? That's just Vy is dy dt. It's a different way to write it. That's all it really is, but it kind of indicates what the next step is, though, okay? So now what you can do, so the change in y is equal to 2 times whatever the time is times the change in time. Okay? So that's the next step. Because you've got differentials there, a dy and a dt. What you want are variables that you can work with, see? So what you want to do to get variables now is integrate. So the integral of dy is the integral of 2t dt. All right. Now, when you look at this, we're going to integrate, so I want to put limits here. So I'm going to go y and t. Now, my lower limits, I've got to look at the problem statement, and what it tells me is that when t is 0, the particle starts to move from coordinate 0, 4, there it is. Okay, so when t is 0, y is 4. Okay. So that's what I've been talking about with those limits. You look in the problem statement generally for something that tells you about t and y and relates them together at some instant in time. And in this case, when t is 0, y is 4. Okay. Then you can integrate. Okay. So the integral of dy is y, and the integral of 2t is t squared, and that's from 0 to t. So what do we get here? We get y minus 4 is equal to t squared. Okay. Now what we want to do is we want to relate x to y. So I think what we want to do here is take a square root of this, both sides here. So I'm going to get the square root of y minus 4 is equal to the square root of t squared. And that's t. All right. We're good with that? Okay. And then you want to do the same thing on the x side. And what you want to do is solve for t again. Because by solving each side for t, you can equate the sides together is what you can do. So this works out to be x over 2 when you work it out. So that's going to equal y minus 4. So when you work through that, we've got the particle moving just to the right here is what it's doing. So we only have to worry about the positive root, so to speak. So we're going to get x over 2 is the square root of y minus 4. And you can work through the algebra on that. And what you get is that y is equal to x squared over 4 plus 4. All right, so that's a bit of a parabola there. You know, when you plug in 0, you get y equals 4, so that's going to basically do something like that, okay? So what you're doing there is you're taking two relationships with respect to time, and you're converting them into one relationship that relates x and y directly together, so you can come up with a path. We good with that? We got any questions? All right. So that's that one there. Okay. Okay, the last one here that's due, we got a ball pushed along that path. Y equals 3x to the 1/2 by the bar. The bar moves it with a constant y velocity of 0.27. Now get used to translating these sentences. So v sub y, and what that is dy dt, right? That's 0.27. That's what that says. Okay. The system starts from rest with the ball at 0, 0 when t equals 0. So that's going to help us with our limits. Find the x velocity of the ball at a time of t equals 11 seconds. Okay. So what's going on there is you've got this parabolic path that the ball is being pushed along, but it's pushed at a constant y velocity. But because of the shape of that path, it will not have a constant x velocity. The x velocity will vary, okay? So that's what's going on with that. All right. So what you got going on here is you got dy dt is equal to 0.27. You got some limits. They're pretty straight up, though. It's just 0, 0 when time is 0. So you can work through that, and you'll get to the fact that y is 0.27 times whatever the time is. Okay. Now we've also got that y is equal to 3x to the 1/2. Okay. So you ought to be able to plug in what y is. Y is 0.27t, and that equals 3x to the 1/2. You okay with that? Just a little step by step here. So what we've done there, we started off with a path, y is a function of x. We also had the relationship between y and the velocity. We can work that to get a relationship between the y velocity and we have the y velocity. We can work that and get a relationship between y and t. Okay, so we got a relationship between y and x, and we also can figure out a pretty simple relationship between y and t. So now we can figure out what the relationship is between x and t. That's kind of the path that we're following to get this thing figured out. Okay? So what you should be able to figure out from that is that x, the position x, is equal to 0.0081 t squared. Okay? And once you've got that, we should get that dx dt, which is v sub x, is 0.0162 times whatever t is. So when t is equal to 11, Vx comes out to be 0.178 meters per second.
Yeah, 11, you just wrote down 1.
Oh, thank you. There we go. So you got any questions on that one? So that's a bit of a run through the homework there. Okay. All right. We got a little bit of a typo yesterday about the homework there. This should be 134. Sorry about that. And it's already correct in Moodle. So 134 is on a separate page, I think. It's on. It's in the notes, and it's 4C. It's on page. Is that 4C? Page 4C. So it's there. That one might be a little interesting, part 2 anyway. You might want to use a spreadsheet or something for part 2. We could go over that when, maybe Tuesday or something. Okay, so I'm sorry about that. All right. All right. Now let's look at some other ways of doing this rotational stuff. There's other coordinate systems that are used. It's actually pretty unusual to do this stuff in Cartesian coordinates. It's hard to work with. So there's other approaches that we use to get this stuff figured out when we've got curved motion. Okay. So why don't we have a look at some of this? This is on page 180 is where it's at. So here's another set of coordinates. I don't know if you've worked with these yet. They're called normal tangential coordinates. So why don't we have a look at that? Okay. And this is let's just look at some simple rotation here. So let's say I've got a weight and I'm spinning it on a string, or I've got an old album, an LP album, they don't really hardly make any more vinyl, I guess they call it now. So yeah, I put a dot on the edge of the record and put it on a turntable and spin it. And, we're talking about something like that. So just a simple circular rotation. Okay, now the circumference of the circle is 2 pi r, okay? So that's how far around the circle it is. All right, now if we've got a certain angle that we're taking up here, call it theta, the total angle in radians would be 2 pi. So if we measure that angle theta in radians, the arc distance corresponding to that angle would be the circumference of the circle, 2 pi r, multiplied by the proportion of the circle taken up by the arc, which would be theta divided by 2 pi, because there's 2 pi radians in a circle. Okay? So if we multiply that through, we'll get a relationship here between the arc angle and the distance around the arc. And there it is. So S, which is the curved distance around the arc, is the radius of the circle times the angle of the arc in radians. Nice simple relationship there. And what you can do is take that a step further and look at something rotating around that arc at a certain time and divide both sides of the equation by t. Okay? And what I'll get is S over t, which would be the speed of something going around that arc, so that would be the velocity, would equal r times theta over t, which is theta dot, which is the angular speed in radians per second. Okay. So what we've got here, if we've got a car that's traveling around a little section of this cloverleaf intersection, what's happening there is there's a relationship between the angular speed of the car and the linear speed of the car as the car goes around. So if the car's doing that, as it works its way around, there's a relationship between that velocity and the angular speed as it works its way around. Okay? And that relationship there is the velocity is the radius times the angular speed. Now, if you took physics, I don't know if they use theta dot. They probably use omega, would be my guess. So theta dot and omega are the same thing. I'll just point that out. Okay. Right now, if we make something travel in a circle, okay, and if it's traveling at a constant speed, let's just have a look at what it's doing there. What it's doing, if it's going at a constant circle, in a constant speed, so if I'm just spinning a weight at a constant speed, is there is just a constant speed as it rotates around. Now, if I look at that constant speed, one thing that isn't constant about it is the direction, okay? So the direction will change. Even if that thing's always moving at 3 meters per second, its direction changes. And if you look at that, if you take those two velocity vectors and put them together, as you start to take this angle here between the velocity vectors down to 0, the delta v, which expresses that change in direction, will point closer and closer towards the center of the circle. So as this thing goes around that circle at constant speed, it's constantly moving in towards the center of the circle. I think of circular motion as something that wants to go straight, but something won't let it. Something keeps pulling it in as it's trying to go straight. So even though the Earth doesn't move in a circle, you could think about it that way. The Earth has all this inertia. It's trying to keep going one direction, but the sun keeps pulling it in. Now, it never gets any closer because what's happening is the direction only is changing. It's staying that constant distance away, but it's always being pulled in. It's kind of a odd thing there, but that's what's happening. That's what curved motion is. Any type of curved motion requires a force to push or pull the object in towards the center. Whether that force is gravity or a string that's pulling this weight in, or a connecting rod on a piston, or whatever the heck it is, there's got to be something pushing or pulling the object in towards the center. Okay? All right. Now, if we want to figure out more about this relationship, we can find some things out about it here by setting up a ratio. Now, what we've got here is this velocity, even though the magnitude of the velocity is constant, the direction changes. So that is a change in velocity. And a change in velocity is an acceleration. Now in physics, I think you'd call this centripetal acceleration, but we're going to call it normal acceleration, okay? So they call the angular speed omega, and we call it theta dot right now, and they call this centripetal acceleration, but we'll call it normal acceleration. It's normal to the curve is what it is, and towards the center. So if we want to figure out what that is, we can set up a little bit of a ratio here and compare the ratios. Because what we've got are two similar triangles that are shown on this page. We've got the similar triangles between the radii. So we've got the two radii that have the same magnitude and an angle in between them. That triangle there with the delta r going from one endpoint of the radius to the other is similar to the velocity vector triangle with two velocities of the same magnitude, the same angle in between, and delta v. Okay? So you can set up a relationship based on those two triangles that delta v is to v as delta r is to r. And then you can solve it for delta v. Delta v is v delta r over r. I'm just multiplying both sides of the equation by v there. And then realize that that acceleration, that normal acceleration, is delta v over delta t, the change in velocity, which is a directional change, divided by the time in which it occurs. So if I divide the left-hand side of that equation by delta t, I also divide the right-hand side of the equation by delta t, and I've got a delta r over delta t, which is a v. So what I end up with for that normal acceleration is v times v over r, v squared over r. Okay? So the normal acceleration has a magnitude of v squared over r, and it accelerates in towards the center of curvature. Okay? The velocity is r times theta dot, the angular speed, and it's tangent to the curve. So that's kind of the things we want to remember from what we just went over here, right there. Okay. All right, so that's about what we got time for here, I think. What, you got those 4 homework problems due tomorrow? And then we'll keep going over this stuff tomorrow too, okay?